Hello, today we're continuing in our GCSE Physics Revision series looking at X-ray production and use. First, how do we produce X-rays? We take a glass tube. This is a sealed glass tube. So this is glass. And we evacuate it. That is, we take all the air out, or as much as we possibly can, so that there's a vacuum inside the tube. Then we take two electrodes. These are of course just metal plates, and we connect them not to a battery as you might imagine, but instead we connect them to 100,000 volts supply. Now you won't get that from the mains. In the UK you'd get 250 volts. So you'd need to put this through a step-up transformer, a 400-fold step up from 250 volts to 100,000 volts, so that you've now got a very large potential difference across these two plates. This will be the positive plate, and this will be the negative plate. And you put a heater behind this plate. These plates have got names. The negative plate is called the cathode, and the positive plate is called the anode. So what is happening? The cathode is a metal and it has free electrons in it. The heater is heating those free electrons and giving them energy, and there is a huge potential difference between these two plates. Ordinarily, of course, no electrons would flow across this gap if it were filled with air or any other kind of gas, because that would act as an insulator. But if you've taken all the gas out and there's a vacuum in here, and you've got high energy electrons here, and you've got a huge potential difference across the two plates, what actually happens is that electrons will, as it were, jump across from the cathode to the anode. They are attracted to the positively charged anode, so a negatively charged electron will be attracted to the positively charged anode. These electrons will have very high energy. We normally measure energy in units of joules, but for these purposes we create a new unit of energy. If you take an electron and you accelerate it across a potential difference of 1 volt, so if this is plus 1 volt and this is naught, and you have an electron which is of course attracted, that will be relatively positively charged, that will be negatively charged. If the electron is attracted to the positively charged plate and crosses a gap of 1 volt, we say that its energy is equal to 1 electron volt, simply because 1 electron has jumped across a potential difference of 1 volt. Well, here we've got an electron that is jumping across a potential difference of 100,000 volts. So the energy in the case of our electrons is going to be 100 keV, 100,000 electron volts of energy. And that's a lot of energy. And what we do is we arrange for the anode to be shaped something like this, and it's made out of tungsten. Tungsten has the chemical symbol W, and there are 74 protons in every tungsten nucleus. And what happens is these very high energy electrons hit the tungsten anode, and for reasons I'll tell you in a moment, you get X-rays coming off. One problem is that only 1% of the energy goes into the manufacture of X-rays, and the other 99% of the energy of these electrons is converted into heat. And so hot does the anode become that it could melt. Consequently, you have to think of ways of cooling it down, either by passing water around it to carry the heat away, or sometimes the anode is shaped like this on a spindle so that it's spinning like this. The electrons are always hitting the lower part, which, because it's spinning, means that different bits of the anode are being hit, so it doesn't heat up as much. Now, why is it that these high energy electrons, when they hit the tungsten anode, produce X-rays? Well, there are two reasons. The first is that if you think about a tungsten nucleus, it's got 74 protons and they are all positively charged. So there's a high positive charge in the nucleus. Here comes a very high energy electron, which is negatively charged. So a negatively charged electron will be attracted to the positively charged nucleus. It won't be stopped because it's travelling too fast, it's huge energy, but it will be slowed down and it will be diverted as it moves towards the positively charged nucleus. And that means that it both changes direction and slows down. And as it slows down, it loses its kinetic energy, and that energy is converted into X-rays. And that is called braking radiation, or in German, Bremsstralung. Bremsstralung actually means braking radiation. So we don't talk about Bremsstralung radiation because that would be braking radiation. And depending on the extent to which the electron is diverted, obviously the further away from the nucleus it is, the less it will be diverted, so the less energy it loses. The consequence is that the X-rays that are produced cover a range of frequencies. So if we plot the intensity of the X-rays that you get out against the frequency of those X-rays, then you get a kind of a chart that looks something like that. So a range of frequencies of X-rays. The higher the frequency, the higher the energy. Energy is associated with frequency. So the higher energy X-rays are at this end. The lower energy are at this end. And you don't really want these. Why? Well, let's just think about how you're going to use your X-rays. You're going to have a kind of a table, and the patient lays on the table. And the idea is that you put an X-ray machine above them, and you have some kind of photographic plate, or as we shall see later now, modern charged coupled devices which are electronic. And the idea is that the X-rays pass through the patient and hit the plate. But as they go through the patient, they will be what's called attenuated. That is to say, their intensity will be reduced. And by how much it is reduced depends on what they go through. If they go through flesh, they don't lose very much energy, therefore they're not very much attenuated. So when they arrive at the plate, there's still a lot of intensity. If they go through bone, then they will be heavily attenuated, and consequently they will be very much less intensity when they hit the plate. So what you get on your plate or your charge coupled device is a series of intensities which shows what the X-rays have been through. But clearly you need the X-rays to go through the patient and hit the plate. Otherwise, you don't get any record of what's happened. Low energy X-rays will be absorbed by the patient and won't ever get through to the plate. And that's a complete waste of time. Firstly, because you get no record of what that X-ray did. And secondly, because you're exposing the patient to X-rays, which have a danger, but for no benefit. So really you want to get rid of the low energy X-rays. And that is usually achieved by putting some kind of screen at this point here, which filters out the low energy X-rays and only lets the high energy ones through. So Bremsstrahlung, or braking radiation, is the main means by which the X-rays are produced. But there is a second means. Here is the tungsten nucleus, and of course orbiting that nucleus will be electrons, and they will have different energy levels. So let's take an electron here, and suppose a high energy electron that comes from the cathode towards the anode hits that electron. It might give it energy to promote it to a higher energy level. And so the electron will now be in a high energy level. But nature doesn't like sitting at high energies. It much prefers to return to low energies. So after a very short time, the electron falls back to the lower energy level. And as it falls back, it gives off the energy, which is the energy difference between this level and this level. And that's a very precise amount of energy. We call it delta E, to represent the change in energy between this level and this level. And that becomes a very specific frequency of X-ray. when electrons fall down from higher energy to low energy, they don't always give off X-rays. Sometimes they give off ultraviolet, sometimes they give off visible light, sometimes even infrared. It just so happens that in tungsten there are energy levels where the difference in energy equates to the X-ray region. But they are very precise frequencies for that energy transition. And if you had another electron energy level here and you went there, that's a different energy. That's a greater energy than this one. And that will give you a different frequency of X-ray. So the consequence of the high energy electrons coming in, hitting an electron in a tungsten atom and promoting it to a higher energy, then that electron falls back to its original energy level, gives off that energy in the form of an X-ray, and the frequency of that X-ray is wholly determined by the energy difference between the promoted level and the normal level of the electron. And so what you then find is that if you now take this graph which shows the intensity of X-rays against the frequency, the braking radiation, or the Bremsstralung, gave us a smooth curve, something like that, superimposed on which are spikes, which represent the specific frequencies that you get from this process here. So two types of X-rays are coming off, the smooth curve, which is the braking radiation, and then the added spikes, which represent the specific frequencies you get for quite specific electron jumps from a higher energy level to a lower energy level. So what happens when X-rays go through the body? Well, they are what's called attenuated, which means they lose some of their intensity. But you still need them, as we've said, to get through the body and onto the plate so that you can see what's going on. The thing is that the absorption of the X-rays will differ depending on what the material is that they're passing through. The intensity, if this is the thickness of the body material, as it were, then if you're talking about muscle, then the intensity will reduce as the thickness of the muscle increases, the intensity reduces, but it doesn't reduce by much. Whereas if it were bone, the intensity would fall off very much more rapidly. For a relatively small thickness of bone, the intensity would be here. But that intensity for muscle would be achieved with a much greater thickness. Consequently, when the X-ray hits the photographic plate or the charge-coupled device, if it's gone through bone, it will be at a much less intensity than if it's gone through muscle. And that gives you a picture, a very clear picture of the bone structure, of the muscle structures, and if you've got a breakage of a bone, that will show up very clearly. In the old days, of course, they used photographic plates because when X-rays hit photographic plates, they expose them in the same way that light hitting a photographic plate will cause it to change. But these days, you're much more likely to use a charged coupled device, or CCD, and this is made up of a series of silicon chip pixels. It's essentially a very, very large grid of these silicon chips, and if light, or in this case X-rays, hits a particular little cell or little pixel, it generates an electric signal, and the strength of that electric signal will be proportional to the intensity of the X-ray hitting it. And so consequently computers can take the information that's coming from all these pixels and translate that into a picture on a television screen. This produces a very clear and a very sharp image. It's exactly the same technology as you have in your digital camera. You no longer use photographic film, instead there is something like a charge-coupled device which is recording the information of the light that is striking each of these pixels in order to produce a very sharp and focused image. So how can we use X-rays? Well, firstly, of course, for medical diagnosis. We're using the high-frequency X-rays. High frequency is equivalent to high energy. those X-rays will pass through bodily parts, but they will be attenuated to different degrees depending on what they're passing through. They will not be attenuated so much if they're going through body tissue, but they will be attenuated a lot more if they're going through bone. The intensity of the X-rays will be recorded on a photoplate or on a CCD sensor, which is similar to a digital camera. And these can be used to check, for example, whether you've broken bones. They're also used, of course, to take X-rays of your teeth. Normally, an X-ray is a one-off picture. So it's a single X-ray picture. But there is such a thing as a CT scan, or sometimes a CAT, C-A-T scan, which stands for computerized axial tomography. And the idea is that you put the patient, and this is as it were looking end on at the patient, and you have an X-ray machine and an X-ray detector. So this is where the X-rays are produced, and this is where they will be detected. But the idea is this whole thing can swivel round. So you start by taking a picture like that, and then you take another picture where the receiver is here, and then you take another picture where the receiver is here. So effectively you're taking pictures through different parts of the body. And that enables you to develop a 3D image. So the X-ray device is constantly turning, and as it turns it takes pictures. And the computer is actually able to develop a three-dimensional image of what's going on inside you. But as we shall see in a moment, that of course is lots of X-rays. So you are being exposed to a lot more X-rays than for a single X-ray. There's also a process called fluoroscopy, where you will be invited to drink a solution made up of barium sulfate, which is a kind of chalky fluid, sometimes called a barium meal. And the idea is that that will go into your stomach and early parts of your intestine. But barium sulfate will absorb X-rays, so you then get an X-ray taken, and that will show up where the barium sulfate is, which is a liquid. And if there are any problems, then that will tend to highlight them. You can also have something which is a little bit worse called a barium enema, where the barium sulfate is injected at the other end, and again an X-ray is taken which shows if you have any problems in the lower part of your digestive system. But X-rays can be used also in treatment, not just diagnosis, in a similar way to the way gamma rays were used. In this case, you might have a patient with a tumour, and what you have, as with the gamma ray process, is an arrangement whereby the X-ray device goes round in an arc, firing X-rays at the tumour, so that the tumour gets all the dose of the X-rays. But of course what you're trying to do is to kill the tumour, but you don't want to kill the healthy cells in the remainder of the patient. And if you do it this way, it means that although the tumour is always the focus of those X-rays, as the X-ray machine goes round, different parts of the body receive a much lesser dose than the tumour itself. For example, this bit of the body is only getting radiation when the X-ray machine is here. And when it's everywhere else, this part of the body isn't being exposed to X-rays. But the tumour gets the full dose, and therefore you can try to kill the cells, which is what you're trying to achieve. As we've seen before, people who use any form of radiation, which is ionising and can damage cells, need to take precautions. So radiographers who operate the X-ray machines must minimise their exposure. They will wear lead aprons, they may stand behind a lead screen. In the case of dental operators, you may find they even go outside the room whilst they take the X-ray. And for patients themselves, there are often lead coats that you put on them for all parts that do not need to be exposed to X-rays. So you only X-ray the bit that you need to X-ray, and you protect the remainder of the patient with some kind of lead coat. The safe amount of exposure to radiation is called dosage, And different types of radiation, alpha, beta, gamma, X-ray, have a different effect depending on the extent to which you're exposed to them. And so to bring them all into a common standard, there is a thing called an equivalent dose. And that is measured in sieverts, or SV for short. And the higher the dose you get, the higher the chance of biological damage. And it's generally reckoned that if you got 0.25 sieverts, or 250 millisieverts, in a single day, you might start to encounter things like radiation sickness, nausea, and some cell damage. So you want to make sure that you keep well below that limit of 250 millisieverts in a single day. In fact, people who operate X-ray machines or other forms of radiation usually have to keep below 20 millisieverts per year over a period of 5 years, with a maximum of 50 millisieverts in any 1 year. As far as a patient is concerned, a dental X-ray probably only gives you 0.0005 millisieverts, so very low dose. Whereas a full body CT or CAT scan will give you 15 millisieverts, which is pretty close to the average annual maximum amount for a radiographer. So you can see that on that basis, it's unlikely that they will want to repeat a CT scan, because then you will be getting a very high dose of X-rays. Fluoroscopy, the barium meal or the barium enema, is about 5 millisieverts. There was a nuclear accident in Fukushima in 2011, and the people living close to that radiation accident were probably exposed to 68 millisieverts, which you'll see is beyond the maximum dose that medical operators are expected to get. And just to put it into perspective, as I've said before, we are all exposed on a daily basis to background radiation from outer space, from rocks, from food, and that is about 2 millisieverts per year. So the background radiation per day is very small.